From Photonics Media, this is All Things Photonics, a podcast shedding light on industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, our hosts speak with luminaries, rising stars, and market leaders about the trends shaping the current and future landscape of photonics. From space and deep-sea exploration to precision timekeeping and advanced manufacturing, this is the podcast for progress on All Things Photonics. This season of All Things Photonics is brought to you by Polyscience and Thor Labs.
Today's episode is brought to you by Polyscience. For over 60 years, the Polyscience line of award-winning temperature control equipment has been helping the photonics industry reach its goals safely and efficiently. Our products are made in America and delivered globally. Please visit polyscience.com to learn how we can help you. Changing the world of chillers is more than a tagline. It's a part of our history. Today's episode is also brought to you by Thor Labs, a global designer and manufacturer of photonics technologies. We provide a comprehensive portfolio of over 22,000 stocked items for same-day shipment, complemented by endless custom solutions enabled by our vertical integration. Visit thorlabs.com to learn more.
So there's two things that you probably noticed about this episode of All Things Photonics. One of those being pretty significant runtime. And the reason for that is probably some of the other things that you noticed. We have two photonics luminaries on our hands, and we have our first knighted guest. Our conversation with Sir David Payne clocked in around 45 minutes and could have easily gone quite a bit longer. Our conversation with Dr. Tara Fortier clocked in around half an hour. Given that this is the season finale, we've decided to air these interviews with minimal cuts. Our first guest, Sir David Payne of the University of Southampton, is known for his significant contributions to fiber optics and fiber lasers. Between the 1970s and the 1980s, his research work helped to push fiber optics into a place where they could connect the world by spanning oceans and scaling mountains. His work in fiber lasers, as you'll hear, broke similar barriers, namely the kilowatt output barrier. Following that interview, senior editor Joe Kaczynski speaks with Dr. Tara Fortier, project leader of the Time and Frequency Division at the National Institute of Standards and Technology. Fortier's research focuses on precision optical and microwave metrology, as well as the development of optical clocks. In this conversation, you'll hear about her group's current projects with ultra-precise timekeeping, a primer on quantum networking as it relates to timing and frequency, and plenty more. But first, my conversation with Sir David Payne, director of the Optoelectronics Research Centre at the University of Southampton. As a vehicle for communication and data transmission, fiber optic cables are pretty commonplace, but that wasn't always the case. Can you tell us about the progress that you and your team made during the 1970s that sort of pushed fiber optic cables into the realm of usefulness?
Yeah, pretty well everywhere is an understatement. Yeah. There are 5 billion kilometers of fiber installed worldwide. Under the oceans, across the oceans, over the mountains, continents, everywhere. In this huge cobweb of global fibers, which drive the internet. Without the fibers, the internet doesn't exist.
Right.
They're being installed at the moment something like 500 million kilometers per year, which is an incredible number. And the other thing that I like to tell people as well is that the price of optical fibers is in the region of $3 American per kilometer. For the best waveguide, the best communication medium the world has ever seen. Isn't that incredible?
Yeah,
it
certainly is.
It's actually cheaper than spaghetti.
That's something.
Yeah, so back to your question, because I'm one of the lucky people that was here from the beginning, because I knew the Nobel Prize winner Charles Kao, who got the prize for the invention of the optical fiber for telecommunications, in particular the use of silica. back in 1964 when he published his first paper, and I started my PhD as what I believe as the very first PhD student in the world on this topic. And that was in 1967. And the idea was that everybody thought the Brits were crazy because we were the only guys working on it at the time. And we had no idea how low the loss could get, because it's very difficult to measure any material that the loss is so low, unless you've got a kilometer, which you didn't have, right? So, you only had pieces of glass that were maybe 10 centimeters or so. And trying to measure the loss in 10 centimeters is very, very hard. And so we didn't really know what the losses were going to be. But Charles Coward pointed out that it was probably impurities that were in the glass. So we had to purify the glass, and we ultimately managed to do that through a process of distillation, which is still a process used today, of the precursor materials. So galloping through the history, because otherwise we'd be hours. So the Brits started this all off when there were groups formed around the UK, mostly commercial, involving the British Post Office as it was then, who didn't quite believe in it themselves, actually. I have a famous comment from the head of their research department saying that it might see some limited applications. Telcos have a habit of doing this. You follow history, by the way. But anyway, so work started like this, and eventually people started to join in. The great Bell Labs, of course, were thinking, nah, we don't think this is going to work. So they were working on a series of relay lenses, right? Laser beams and relays of lenses. Crazy when you look back at it. But they thought the fiber was crazy, so everybody was calling everybody else crazy. And then Corning came in, of course, and what had happened there was that the ideas had jumped the Atlantic because Corning acquired a British company that made silica called Electrocell, who had a contract from Charles Cowell. And so they thought, well, we know how to make silica. So they take the credit for the very first practical demonstration of an optical fiber, albeit their first efforts were pretty poor compared to today's, but it was a sensation because it proved that you could get down to what they were reporting, which is 20 dBs per kilometer, which, by the way, that's 10 times what a standard fiber is today. Right. But everybody went crazy and said, this is possible, my God, it's possible. And so everybody piled in. The Japanese in particular came in, did magnificent work on production techniques. Corning themselves have a massive, and one of the few remaining manufacturers, by the way, in the world. The rest are all Chinese, major producers of optical fibers, and one Indian. So that's it in a nutshell, very, very quickly. But I've skipped over 20 years of development there to where we got to, and where we are today, where the conventional fiber is so refined now, its loss is about 0.15 TBs per kilometer, which means that you need a repeater or a booster every 60 to 100 kilometers.
Sure. Actually, I was wondering if you could expand on that, the need for a repeater or a booster. Why is that?
Well, because of the loss of the fiber, you put light in one end from a little semiconductor diode laser, and the light dims because of the losses. And so it gets fainter and fainter until after 100 kilometers, there's almost nothing left. So there's no light coming out, there's no photons, or very, very few. And you're now below the noise of the detector, so you need to boost it up before you get to that sorry state. And so what they do is they put in an optical amplifier, every 60 to 100 kilometers. So that just boosts it back up to the starting intensity, and now it decays again over the next 100 kilometers.
Right.
So whenever you see an optical fiber link, just bear that in mind. If it's going undersea, you've got buried repeaters, amplifiers, optical amplifiers, every 100, well, usually about 60 kilometers undersea. And this is part of my history as well, because we are credited with the very first announcement of an optical fiber amplifier from Southampton, which is where I have done my work. And we looked at this problem in the 1980s because everybody, not just us, had realized that we need some form of amplifier to go the next span. And people were working on, everybody realized electronic amplifiers weren't good enough because they're too slow. And they also tend to mix up the different colors or channels, if you like, within the optical fiber on the detector. So nobody wanted to use electronic amplifiers. So everybody was looking for some way of optically amplifying, and people were looking at diode lasers, and you stop the reflections and they become amplifiers. Or there was a Raman amplifier, which was fairly well known. And then we came along and announced that if you put erbium into the core of the fiber, pumped it with a little diode laser, you could make a very efficient and effective amplifier within the fiber itself. So you look at the fiber, you wouldn't know that it's an amplifier in it, right? And that was a sensation, and that was announced in very early 1987 at the OFC conference in Reno, in Nevada, by ourselves in a post-headline paper. And the world went mad at that point, and I'm often blamed, by the way, for creating the dot-com boom.
Oh, yeah.
Because what happened was everybody piled in because everybody could immediately see this thing can now go global.
Right.
It's not just a local thing, it can go global. We can go across the oceans because we just put amplifiers in. We got the amplifier at long last, and now let's just pile in and stuff as much of this fiber as we possibly can in. And so everybody started up companies and started producing this stuff as fast as they can. And the predictable happened, of course, is that we put too much in. We overshot the market.
Right. And, as we tend to do.
As we tend to do. Well, you know, there's a lot of money that is floating around. The VCs would give you any amount of money to
right.
We were rolling out the internet, you know? It's a bit like American history, of course, the same thing happened over the railways.
Yeah.
You know, there was a huge boom and bust as a result. We were rolling out the internet, just like the railways. There was a boom and there was a bust. So, you look at the stock prices, they exactly match the amount of fiber that is going in until we overshot, and then the stock prices all crashed.
Right.
Yeah. So in my history, I've seen lots of ups and downs.
So now that we have cables that can connect cities and span oceans and go over mountains, what are the current frontiers in fiber optic communications? How is that technology being pushed forward today? And I guess, what's the role of the Photonics Hyperhighway project in those efforts?
Okay, well, that was actually followed on by another project with a similar name. And we've currently got a project called FastNet. So to go back to your key question, because you might think from what I've described that the game is over, right? We've got 5 billion kilometers spanning the globe. We're sticking it in as fast as we can. Job done. Well, actually, the demand exceeds the capacity of the fibers, and nobody wants to it's expensive to put more and more and more and more fiber in. What you'd rather do is to make fibers with more and more capacity, so that you didn't have to keep putting in more and more fibers. And there have been a number of attempts at that. So the current so-called silica fiber with a solid core of germanium-doped glass dates back to probably the early 80s as being stable. And the companies have tweaked and done tiny refinements. But we've had pretty much the same fiber for 20 odd years now or more. And so we were all staring at what do we do about this? And so one of the things people started to do was put multiple cores in the same fiber. And that has a penalty, of course, because it's more and more difficult to joint them. You've now got azimuthal alignment that's required, and they're harder to make. And actually, the cost goes up roughly as the number of cores that are in there. So it wasn't a full solution, and it got you a factor of 5 or something like that, which was, it's not a big number. The rate of growth of the capacity. Right. So the very latest thing, once again, came from my labs here in Southampton, which is let's get rid of the core altogether and replace it with a hole. And everybody is probably thinking, well, I thought fibers worked on total internal reflection, so I got to have a core of higher index, haven't I? That's what your textbooks will tell you, and they'd be right. But we can use structures inside there, resonant structures. And it's a thing called an anti-resonant structure that we actually use in there. So it's a little bit like putting tiny reflectors all the way around the core that bounce the light back into the hollow core, which is either vacuum or air or some gas or other. And it's a bit like my colleague Francesco Poletti, who is one of the pioneers of this technology, often refers to these as bars in a cage, a gorilla's cage. They keep the gorilla inside. So my explanation is probably inadequate, but for the moment that'll do. And so what this means now is that the optical signal, the light, is traveling entirely in the air that's in the middle of the hollow core. No glass. So because there's no glass, you can get a lower loss, even lower than the amazing solid core fibers. And because there's no glass, all the impairments in transmission, such as distortion and dispersion and things like that, which happen in fibers, unsurprisingly, when you're going through effectively 100 kilometers of glass, don't exist anymore. And so, the capacity of these fibers is much greater as well. And these have only just emerged. And about a year ago, we reported that the loss in the fiber was better, lower than a conventional fiber. And this is another sensation, and everybody started to work on it like crazy. So watch out for the next .com boom, right?
Right. Sir David's at it again.
Yeah, so that's what's going on at the moment. And of course, we need to reset our minds, I've been in this field now for 60 odd years, and you get ingrained in your mind certain things. So you talk to any telecoms engineer and they'll say, oh, well, an optical fiber works at 50 nanometers. And they'd be right. That's the lowest loss point in a standard solid core fiber, but not in a hollow core fiber.
Right.
No glass, right? So all of a sudden you can work at pretty well any wavelength you want within limits. And so we've opened up the window, and we haven't quite got, certainly in my case, I'm still thinking 1550. I shouldn't be. I should be thinking 800 nanometers, why not? Or maybe 1300, or maybe 1800, 2 microns, why not? Why not? And that, of course, then has this knock-on effect, exactly as the amplifier originally did, by people asking, oh, do we have the right components to drive this new system? Do we have the detectors? Do we have the transmitters? Do we have all the 4-port couplers and coupling mechanisms and cabling and all the rest of it? So it's the whole rebirth of optical fiber technology right from the beginning again. The big advantage, Joel, is that I know what's going to happen because I only just look at what happened exactly 20 years ago.
Right.
So you know what? That's what's going to happen next, and that's what's going to happen next. So the advantage of all this is I'm just recycling all my papers. So, yeah, but we're having a lot of fun.
I have what may be kind of a silly question. Keep in mind, I'm a layman. My background is in, writing. But with the hollow core fibers, what's in the hole? Is it a vacuum? Is it a gas? And does what's in the the hollowness of the fiber, does that affect the signal?
Well, that's actually an amazingly good question, Joel. So, because you're right, what you put in the core, a gas now, not a glass, it's got to have some effect, hasn't it?
Right.
And it does. But they're a much lower level, of course, than they would be in a glass.
Sure.
Because nonlinear effects and all these other effects are much lower in gases. But they're still there. And this is exciting to explore, and we are exploring it. So the first thing to observe is that when you draw these fibers, who knows what's in the core as a gas? Because you have the gas that you put into the preforms, and some of that gets into the fiber. Some of it comes and outgasses from the glass itself. And so there's a whole period of study that we're doing, which is saying, well, just what is in there? And being quite surprised at the answers. And just so that your listeners will understand, there's no way that you're going to be replacing by pumping in some gas when the thing's 100 kilometers long, right?
Right.
It's going to take you weeks, months to pump through this tiny little hole. So you're pretty well stuck with what you drew in the core. But it's not a problem in terms of deploying these, because it should be said that we already have deployed these fibers in London. Why London, you might be asking? Well, we started a British company called Luminicity, which was acquired by Microsoft recently. And of course, the people that really, really, really love this stuff are the traders. Why? Well, signals travel faster in a gas than they do in a glass, right? And so the signal gets between the trader's computer, who's placing a bid, to the stock exchange faster than his competitors. And they love that. Particularly for automated trading, where the delay to the exchange makes all the difference. So the first deployed in London underground is in that area. But there's a number of other systems coming up in China, US, places like that. So we're at that stage where we were in the late 70s, early 80s, at the beginning of the early stages of the dot-com boom. Hence the parallels. So we're working. It's one of the topics we're working on right now, and we have an expert called Natalie Wheeler here, and she's an expert on trying to find out what's in this gas. And of course, one of the things that you can then do is use these fibers for something other than telecoms. So you can use them as sensors, for example, maybe as gas sensors. You can use them for nonlinear generation by putting in some interesting gases into the core. And the other thing about these fibers is that they are remarkably stable in delay. Because again, in a conventional fiber, the temperature change varies the refractive index of the core quite substantially. And with no core, that doesn't happen. So you can make very, very stable transmission times for pulses, particularly for things like synchronization, navigation, and things like that. So those are just some of the topics that we're opening up. Not to mention the fact that because there's no core, these things are radiation hard. So really great if you want to stick them up in space.
Sure. Awesome. So now, kind of shifting topics, I guess. Fiber lasers share, a similar level of ubiquity as fiber optic cables. Probably not quite the same level, but comparable maybe in some sense. And another thing that they have in common is that your work led them there. During that early work in that technology's development, what were your goals? What problems were you trying to solve when you were undertaking that research?
So I've already told you that we started shortly after Charles Cowell's amazing paper in the 1960s. What I didn't say was that we were kind of an offshoot from an existing laser group. And that laser group was conventional in those days, in that they were working on things like ruby lasers and gas lasers, helium-neon lasers, neodymium glass and neodymium Jaeger was just emerging. This is, remember, the 60s. So shortly after the laser was actually invented. And as a consequence, and I made the comment already that we got to learn to break out of our mindsets, because our mindset at the time was a laser. So when we were looking for the amplifier, we were actually thinking lasers. And in fact, we published 27 papers on lasers with erbium before we decided to take the mirrors off and make an amplifier. So it shows you that point about how mindset was lasers, lasers, lasers. Oh, we can make an amplifier, was the way it sort of happened. But because of that, after the amplifier, the telecoms amplifier, the erbium-doped amplifier, we thought, well, what else can we do with these fibers? And we kind of figured that maybe we could make some lasers, which we, as I pointed out, we were already doing. But when we began to ask, how much power can we get out of these things? And actually, this work was funded by DARPA because I'd been on a tour around America talking to various military establishments. And uniformly, they said to me, well, you know what, Dave? Anytime we want a long fiber laser that gives out a few milliwatts, we'll give you a call. And that call never came, of course. So until one day when one of the DARPA program managers gave me a call, as her name was Ellen de Varsela. And he gave me this call. He said, Dave, how much power do you think you could get out of one of those lasers? And to be honest, Joel, I had absolutely no idea. But what do you do in these circumstances? The guy's on the phone asking for an answer. I said a kilowatt.
Right.
And he said, really? And I said, classically, it's only a matter of money. He said, I've got money. Now we're talking my language, all right? So he says, well, how much would it cost? I'm not going to mention the amount of money, but it was a lot of money. Sure. But I had no idea how much money it was going to take. But I thought, well, if it's a big target, I would have big money. So I asked for big money, and he said, I've got that much. Send me a proposal, which he did. And within 18 months, we reported over a kilowatt.
Wow.
And once again, it kind of blew the world. And they said, what? And the company started up. We started our own company, which was called SPI Lasers, which is now owned by Trumpf. And of course, there was a guy called Gapontsev, who had a company called IPG, which still exists in the US, high power laser company. And then, of course, dozens of other Chinese companies have piled in and will now sell you. And the same thing is happening. The price erosion is so huge, it's almost impossible to compete in that market. And you're talking about figures of $3 a watt, maybe less. So you want a kilowatt laser, it's going to be three grand. Yeah, it's just crazy. And if you've looked at YouTube, you've probably seen scary videos of these people cleaning rust off cars, off your brake lines and things like that.
Right.
Accidents waiting to happen, in my view, but
Yeah.
that's where we're at. And that's, successful technology has to see that price reduction and that ubiquity of use. So that's where we're at. And I can anticipate your next question, which is what comes next?
Exactly.
Well, we think we know how much power we can get out of a single fiber. And that's in the region of 10 kilowatts, stably, right? So what do you do about that? Well, remember we've now got a medium which we can draw on a fiber drawing machine. And I once calculated you could make about 10 lasers a minute from the amount of fiber that you can produce. And of course, with such a cheap medium, you can do the impossible, which you wouldn't think of doing with conventional lasers. You can stack them together. And how many could you stack? Well, let's just choose a number. Let's say we stack 1,000. And each one's giving 10 kilowatts. That's 10 megawatts, right?
Right.
That's one hell of a lot of power. You can imagine who gets interested at this point. However, it's not quite as easy as that. Because what you've got to do is you've got to phase them together and do what's called beam combination. So for some applications, you can literally just stack them together like that when you don't care about the coherence of the beam and all that stuff. But if you want a pure laser beam coming out at the end of this thing, then you have to learn how to do beam combination. And the most obvious way of doing that is the thing called coherent beam combination, which says you put them all into phase by using little phase adjusters. And the beauty of this is that you've actually then got built in a means of steering, because if you put a linear phase difference across the aperture, it will steer the beam to the right or to the left, as the radar boys. We stole all this technology from the radar boys and girls. So that's the first thing you could do. The second thing you could build in is adaptive optics, because you're going to have to go through the atmosphere, and in some applications a considerable number of kilometers through the atmosphere, and you need to be able to correct the turbulence in the atmosphere. But you've got a mechanism to do this because it's all built in adaptive optics. So that's the next big challenge, is how do you combine, let's say, 1,000 lasers together? What is the best way of doing it? And it won't surprise you to find that machine learning has a lot to offer here, because we've got algorithms now that can synchronize all these lasers together in less than a millisecond, and which is pretty impressive,
Right.
So nobody's demonstrated this yet, but that's the next big challenge, and there's a lot of money around to make what is effectively going to be a laser weapon.
Absolutely. Now, having watched some of your previous media appearances, I understand that the last few questions have been asked of you, quite a bit in one form or another. So I guess with that in mind, could you tell us about some of your work, I guess, outside of fiber optics or fiber lasers, or, maybe something that's still, kind of related, but perhaps lesser known?
Well, interesting. When I've been around in this field for about 60 years, I discovered that you had a lot of ideas, 20, 30, 40 years ago, and they were in the wrong time window. And you tried them and they didn't work. And they didn't work because the rest of the technology that you needed was behind, and it wasn't there yet. So we've talked about the EDFA, the amplifier, and that got poo-pooed by a lot of people because we didn't have the pump diodes to do it. And so when we did it, and when my colleague Emmanuel de Severe in Bell Labs did it, we both used enormous gas lasers, which took 100 kilowatts of power out of the wall plug. These were not practical devices. And everybody's going, oh, well, it's just a laboratory curiosity. And that's just an example. We're in the wrong time window. Diodes hadn't developed yet. And of course, the need for the diodes stimulated their development. But it took a few years before that happened. And so to go back to your question, there were a number of things that I've looked at which just were in the wrong time window. And now the beauty of this is that you can come back to them all again and repeat your publications, and you get it right this time. But I mean, what other interest do I have? Well, I think the gyro, the optical fiber gyro, which, as you know, is very, very important for navigating airliners and spacecraft and all these applications. And we're working with Honeywell at the moment on a new form of optical fiber gyro using, surprise, surprise, these hollow core fibers. Because it turns out that the gyro is performance limited by the nonlinearity in the conventional glass fiber, because we don't have any glass in there. So we've already, in the very early experiments, pretty well matched the results from conventional fibers in a resonant gyro structure as opposed to an interferometric Sagnac type structure. So I've got a lot of interest in there. And once again, and I've made this point already, you got to reset your mind because you don't care about the wavelength anymore. So you can say, oh, what happens if I use a blue diode to drive this gyro? Yeah, I get the advantages by doing that. So reset your mind periodically is what I tell my students. They're in a fortunate position because they haven't got that mindset yet. Right. So a lot of good ideas come from students because they don't think 1550 nanometers for telecoms. They think, why are we working at 1550?
That's one of the benefits of the new crop of scientists coming in is, they don't have ideas that are kind of stuck in their heads. As
I put it, their minds haven't yet been polluted by us older guys.
Right. There's similar things in writing. When you're trying to write something and you're doing it one way, and then if you stop and you say, okay, I'm going to step away from this and then take another look. Sometimes you'll be able to kind of let that idea that was kind of clouding your judgment, out of your head. And
exactly right.
Similar thing.
Yeah. Anyway, I'm not going to give you a huge list of all my other interests, but I do remember that I've been the director of this place, and there's 300 odd staff, and this is all their work, and they're all working on disparate things, hugely different from my amazing colleague Nikolai Zheledev, who's an expert on things like metamaterials, and he's always coming up with these crazy new physics ideas. He's really interested in imaging down at the nanoscale, so we can see viruses with optical microscopes. And he's got all sorts of ideas on how that might be done, and some very impressive experimental results that are heading in that direction. So that's another really interesting thing. I think we're all interested in wondering what the role of optical processing might be in the future. Things are changing. I'd mentioned AI. You can't do a podcast these days without mentioning AI. And AI is important to us for multiple reasons. The first being that it drives the capacity demand on the internet, which we've already talked about, and that's the next big driver. It's going around and scraping all this data off all the world's servers, but also because a lot of photonics processes are very difficult to control. So control with machine learning in the fabrication stage of things, but also in controlling things like the internet. Optimizing the routing in the internet is an obvious application for machine learning, and making it more secure as well is another potential use of AI. And so I'm rapidly generating, as pretty well everybody is now, an interest in what can AI and machine learning do for photonics and the other things that we're doing. And I have a colleague called Ben Mills who's plowing a very rich seam with, he's one of the world's experts on AI and machine learning in photonics. So I'm learning from him a lot. Then there's integration, of course. This is huge. Photonics is one of my favorite sayings: we never have the material we want. And so we've ended up with this kind of potpourri of different material platforms, and it's a mess. And they're not compatible with each other, and they can't be deposited with each other for various reasons. And this is a problem, and we'd love to be able to emulate what the guys in silicon processors do, and just make everything of millions and millions of components all in a little chip. And we're so far away from that in photonics. We think if we get 5 components in there, it's a miracle. And but that stuff is beginning to come alive, and people coming up with new ways and new materials. And I should add that if you want to succeed in photonics, you really need to be a materials expert, because you've got to know about the materials. If you don't, and you don't have the capability to try out new materials, then all you are going to end up with is using the same components as all your competitors. And frankly, our friends in China can assemble things a lot cheaper than we can in the West. So the future is not about smarter ways of assembling existing components. It's about changing the components and having the very best components, and that requires new materials, new processes. And everything is driven by hardware. That's another thing that people don't always understand. Most people would say, "Oh, well, the internet, it's all about web science and servers and software." No, it's not. It's about the hardware. The hardware comes first, and then the magnificent software gets put on top of it and does amazing things. And without the hardware, you don't need the software, right? So those are a few philosophical thoughts, but it's what drives me, and to look at the existing way of doing things and saying there's got to be a better way. And that means you must have access to the most basic of physics and materials technologies.
Absolutely. Now, what's something that you're currently excited about? And feel free to take this in any direction you'd like, whether it's a research project you're working on, or research that you've seen going on outside your lab that's piqued your curiosity, mm-hmm. or even just if there's just a movie that's coming out that you're excited to see.
Yeah. Well, Well, that's a tough question. What excites me? Because I think the answer is pretty well anything new excites me. Because the other philosophical way of thinking that drives me and that I learned is very productive is every time something new happens, you ask yourself, what does that mean for each of the different technology sectors that we're working in? And a lot of people don't do this. They're too narrowly focused around that new thing. But it usually has incredible ripple. Let me go to yet another example. Everybody talks about AI and machine learning. We've already discussed that. But, that's been around. We were using forms of that when I was doing my PhD. But what happened was along came the GPUs and NVIDIA and people like that, and suddenly said, well, you know what, we've got the hardware now. And everybody said, oh my God, yes. And they start putting the software on. So it's always that way around. It has to be the hardware that somebody suddenly comes out of the lab blinking and saying, look what I just made. And,
right.
So, that really excites me. All technologies. I'm a bit of a petrol head, so I look at things that are happening in the EV, the electric vehicles market. In fact, I have an EV, the technology is advancing, and every time I look at that, I say there's got to be some room for optics in there. How do we improve that? And then I suddenly realize, hang on a minute, there's optics all over the thing. It's got, modern cars, especially high-end electric vehicles, have got 7, 8, 9, 10 cameras in them. And all the processing that goes with it, and they've got buses in there. Not much optical fiber deployment, I have to say, which is a disappointment to me. But maybe that'll happen because the bandwidth requirements are going up and up, and
right.
And I'm interested, for example, also in the fact that we've kind of reached the limit of the speed of light. And, when I was a young student, I never used to think about the speed of light. It was just fast enough. But now, we've got a global internet, and you want to go round and round, or you want to send signals through to Mars or whatever, and suddenly, hang on, light's not fast enough. So what are we going to do about that? Well, Einstein said not a lot, right?
Yeah.
But it's never accept anything that is the conventional wisdom. Not that it's a great idea for me to challenge Einstein, but there's got to be a way around this, or are we stuck forever with having to accept that it's going to take minutes, hours, years sometimes if we want an intergalactic internet. So So that's an interesting thing. I fear that in my lifetime I'm not going to solve that problem.
Maybe. You never know.
The other one that's really exciting me is something from a colleague of mine called Peter Kazansky. And once again, Microsoft is picking this up. And that's what he calls eternal storage. And these are little chips of glass, the same favorite material of mine, silica. And he's writing with a high-power femtosecond laser little spots of damage, which we call voxels, inside this chip of glass. And he calls it 5D, 5-dimension storage. Why 5D? Because each of these little dots, which are a bit like a CD, the dots, can store information. So we've got X and Y and Z for the 3 dimensions. But what he found was that internal to these little spots, voxels, they were polarization dependent, and that depended on the polarization of the laser that you used to write them. Right. And also the strength of that little tiny voxel, it has birefringence, and this depended upon the intensity. So there's another 2 dimensions, 5 dimensions, which means you've got a massive storage capacity.
Right.
So, within these little chips, you can have many terabytes. And the beauty of it is that, wait for it, they last 100 billion years.
Right.
At least we calculate them to. And one of his favorite tricks is to take a Bunsen burner, a blowtorch, and heat them up till they're red hot. And then you can drop them into water and they still survive.
Wow.
So, and this is for archival storage, and Microsoft has a project called Project Silicon, which you can Google. And that technology was transferred to them, and they're at the prototype stage looking for a next generation of archival storage for storing things like movies, archiving all our movies. This is what a friend of mine called Vint Cerf, who I'm sure you've heard of, founder of the internet, and he calls this digital vellum. Why vellum? Because vellum is goat skin. So maybe you know this. And it turns out that if you wrote, as the ancients did, wrote on vellum, goat skin, rather than paper, it lasts 1,000 or more years. Whereas if you write it on paper, the paper degrades and goes away. So in the British Parliament today, they still write some key documents on vellum, which you believe. Anyway, so that's another project that we're doing, and that's very exciting. And he's done amazing things. Like recently, he wrote his own DNA into the code for his own DNA into one of these chips, and he now comes into my office and he says, "Look, I'm going to live forever." Right. Yeah. So he's got a lot of interest from people wanting their DNA stored forever.
Yeah, that's quite a thought. You get cloned 10,000 years later or something by some
exactly.
aliens,
that's what everybody's hoping. Well, I've thoroughly enjoyed this discussion, and thank you so much for inviting me along.
Absolutely.
Today's episode is brought to you by Avantes. Unlock the power of light with Avantes. For over 30 years, we've delivered precision fiber optic spectroscopy, trusted for custom integration and reliable data. Discover how to empower your application, industrial, scientific, or beyond. Visit Avantes.com and experience spectroscopy solutions that innovate. Today's episode is also brought to you by LightPath Technologies. From concept through prototyping, volume production, and global distribution, LightPath has the optical knowledge and manufacturing expertise to be your optics partner every step of the way. Visit lightpath.com to learn more.
Stick around. Senior editor Joe Kaczynski's interview with Dr. Tara Fortier of the National Institute of Standards and Technology is up next.
Hi, I'm Joe Kaczynski, Senior Editor with Photonics Spectra, and I'm joined here by Tara Fortier, Project Leader in the Time and Frequency Division for the National Institute of Standards and Technology. Tara, thank you so much for joining us today.
Hi, it's wonderful to chat with you.
Yeah, and first and foremost, going into your title, tell me more about the responsibilities of the Time and Frequency Division.
Okay, so the Time and Frequency Division actually has a number of responsibilities. One of their primary responsibilities is the development and the maintenance of UTC, National UTC. So in our division, we spend a lot of time developing things like optical atomic clocks for timing. The Time and Frequency Division also has a lot of work done in disseminating UTC to the United States. So we have time servers, radio stations, etc. Actually, one thing that's pretty amazing is that the time servers at NIST and Boulder actually get significantly more hits than the Google search engine because many of our electronic devices are actually synchronized to the time frequency division. But aside from that, the time and frequency division does a lot of work in terms of innovating in time and frequency metrology, right? So developing new measurement capabilities. Those are necessary for advancing optical atomic clocks, which are going to be kind of the next generation in terms of timing. But the time and frequency division also does a lot of work in quantum computing, which leverages, precision time and frequency techniques for, quantum control of ions for developing quantum gates and doing error correction, et cetera.
Interesting. So now, what is the role of the atomic clock in UTC? And as tech around us and things continue to advance, are there limitations to this?
So atomic clocks are kind of the basis of UTC. So we use atomic clocks to actually define time. So what we do is we use kind of the beautiful, very exquisitely and precisely defined energy transitions in atoms as actually fundamental constants of nature. So we can define a transition frequency in hertz, and we can use the converse of that to define time. Does that make sense? So that's one way that we use atomic clocks. The other way that we use atomic clocks is that, if you want to develop a standard, right? Atomic clocks are not some things where, we can calculate the frequency. We can't know it absolutely. We have to measure it. And so one measurement is never enough. So we maintain UTC internationally actually by having a global ensemble of participation in UTC. So national metrology institutes around the world like NIST have atomic clocks, and they use those to contribute globally to timing. So we use that ensemble of atomic clocks to define UTC and steer it and keep the world on time.
Now, we mentioned a little bit earlier, you got into a little bit of quantum, talking about quantum technologies, and it's been a very kind of hot topic that we're hearing a lot more discussion. Tech is always looking to get smaller. Can you give us kind of the introductory lesson, the 101 to quantum, and what are the advantages of this, and what can this mean in applications going forward?
Sure. So quantum mechanics is basically the physics of small stuff, right? Like elementary particles, quarks, electrons, protons, photons. And what happens at this level, right? At the level of kind of elementary particles is that nature becomes granular and fuzzy, right? So, we have building blocks of nature, right? It's not, a table isn't continuous stuff. It's made up of atoms, right? So that's where the granularity comes into place. But in terms of the fuzziness, this is where quantum mechanics becomes useful. So quantum stuff is fuzzy because it has wave-like nature associated with it. So, we call these wave functions. But one of the benefits of wave functions is that what falls out of it are things like superposition and entanglement, right? And so this idea of the fuzziness or the uncertainty around quantum mechanics actually creates opportunities for things like entanglement. And we leverage kind of this new nature or this new behavior or different behavior of quantum particles to be able to do things like quantum computing, quantum communication, and quantum sensing. And, the behavior is different enough that we are able to create completely new opportunities in this realm, right? So we can use things like entanglement to improve scaling in computation, right? We can help it to reduce noise in sensing, and we can actually use it to create completely new capabilities in communication.
Interesting. And talk to me about a quantum network, because I know when we talk atomic clocks, we talk quantum, all, very precision based. What are the frequency techniques used here with a quantum network and the challenges that it presents?
Okay, so one thing I want to mention is that quantum networks, right? So I think people have a tendency to draw analogies between quantum networks and classical networks, right? And they are similar in the sense that they both use optical fibers and they both use telecom wavelengths, so 1550 nanometer photons to be able to transmit information. But and they're used for networking, remote devices, right? And so those are the similarities, but that's kind of where they end. One thing I want to be clear about is that quantum networks are not going to be used as an analogy to the quantum internet, particularly because the internet has a very strong focus on throughput and bandwidth, whereas quantum networks are focused on fidelity of quantum states. And what when people are building quantum networks, they spend a lot of time detecting single photons. And if you're detecting single photons, that means you have low throughput. But some of the challenges in quantum networks are that you're looking at single photon events coming from different nodes, let's say remote nodes, and you need to synchronize those events at the single photon level, which requires timing at something like the femtosecond level. That's 10 to the minus 15 seconds. It's very, very short. Something like 1 million times better in timing than something like GPS. So some of the work that we do in the time and frequency division actually has natural applications to this. We develop optical signals from atomic clocks that we disseminate over fiber networks to be able to compare atomic clocks against one another, so that we can characterize those clocks, but so that we can also explore kind of next generation applications with clocks. And we'll need that kind of fidelity also in optical networks, because it's not only that we need to synchronize events very well, but we also have to work with high fidelity signals. So in quantum, this focus on fidelity means that, we need to have good control also over things like phase and frequency to be able to get, the highest fidelity, measurements of the quantum signals that come out of these systems. Does that make sense?
I think so. Yes. And these new tools are kind of unlocking a level of precision that we haven't seen before, excuse me.
Well, I'd say that we're going to be working with, potentially with stabilities and with accuracies at levels that are higher than we use for atomic clock networks. But what we're hoping to do is kind of leverage these tools that we've developed for atomic clock networks and try to apply them to quantum networks to really make them a reality.
So is there a similarity then that allows you to transfer kind of the tools from one to the other? Absolutely. And that's this idea of like being able to control things like frequency and phase very well. So that's something that we have to do very well for atomic clock networks to make sure that when we're measuring atomic clocks versus one another, we're not adding errors. And we can use those same dissemination techniques and measurement techniques to help enable quantum networks. This is like, this is kind of a new project for me. And so, I'd say that my knowledge on this is just a touch fuzzy, but I'm really excited to actually do this because it's a way of taking things that you've worked on for many years and then pivoting them and transferring it somewhere else is very exciting. Yeah, kind of seeing that, and I'm speaking to some people before, they always say, if you want to see the future, read the white papers from 10 years ago, right? Because they're scratching the surface, but now years later, we figure out the applications and, who knows what we can unlock with tech we're already using.
Yep.
I want to talk to NIST researchers. I was reading are testing chips on converting light into microwave signals. And very, kind of groundbreaking stuff here. I just want to see do you know how far along these tests are and kind of the current iteration of them?
Okay. So, I can talk to two projects that I know about. So I think it's like optoelectronic conversion is it's very ubiquitous in the photonics world, right? Because, if, we're working with lasers, we want to be able to take those optical signals and convert them to electronic signals for many reasons. Let's say for optical atomic clocks, what we need to do is we have these beautiful atomic systems. They operate at optical frequencies, but much of the technology that we use in our modern day lives is electronic domain, right? So how do you go from optical signals, right, that are oscillating at, petahertz, that's 10 to 15 hertz, that's a lot of cycles per second, right, to something like a gigahertz where we can interface with GPS. So we need to have things like photodetectors to be able to do that kind of conversion. So some of the work that we're doing, it's not so much on development of these in-house technologies, but actually working with collaborators at the University of Virginia. They actually help us we work with them to help design really high linearity photodetectors. And the reason that they're important for our research is that we're working with short optical pulses. So short optical pulses have a lot of photons in a short amount of time. And when that light, is incident on a photodetector, what we do is we produce a lot of carriers, like photo carriers. So these are electronic carriers. But if you produce a whole bunch of them in a very short amount of time, you can saturate your materials, which creates nonlinearities and can reduce the bandwidth in detection, which is a challenge. So working with actually experts in developing kind of semiconductor heterostructures is very useful for being able to produce devices that are linear at high optical power, so that we can have the signal dynamic ranges and we can have, low distortion, so that we can create electronic signals from optical atomic clocks that maintain the fidelity in terms of accuracy and stability of those optical signals. But aside from that, another area where this is really excelling in terms of optical to electronic conversion with kind of photodetectors is in the development of single photon detectors. So they're, NIST are experts in the development of cryogenic single photon detectors. And what these are used for is in things like quantum networking. So quantum communications, right? What we're looking for is these high fidelity signals using the single photon detectors. And how these systems detect single photons is actually they're superconducting nanowires. And when a photon hits the surface, what they do is it creates a slight temperature change that changes the resistance of the circuit, which allows for detection of single photons. And where they're at in terms of that technology is they're pushing kind of the recovery times to make these single photon detectors higher speeds, so that, if one were to develop things like quantum networks, you'd be able to operate them at higher rates. But they're also trying to develop single photon detectors that can resolve the number of photons that are captured right on a photodetector, and that would help to reduce error rates in quantum networks.
So
and,
still,
I just want to mention that, these are the very few things that I know that are going on at NIST. NIST is a huge organization of something like 7,000 people. And so, I can't capture everything that's being done there, but those are two projects that we're working on that I know of.
No, of course. And it's, great to hear about those too. And one thing, because we got back into quantum for a second, and talking about precision timekeeping emerging, as somewhat of a bridge between quantum optics and commercial markets. Like one example, you can buy a CSAC. So what is the next domain you think for that quantum optical tech will achieve kind of commercial success and will be more publicly available?
Well, so one thing that I'd like to see more of in clock development is the middle ground. So oftentimes what I see in terms of things like DARPA projects is that what they're trying to do is they're trying to take a laboratory scale thing with laboratory scale performance and, put it into something the size of a gummy bear. I feel like those projects are generally not that successful. And at the same time, there are not a lot of, let's say, civil or even military applications that could take advantage of that kind of timing capability. What I think will have some market appeal is the development of atomic clocks, that are the same size as current commercially available cesium vapor clocks, but with, let's say, 10 times better performance, right? So, and with the same cost. So if you were able to achieve better performance at the same cost with the same form factor, I think that would have wide application, right? Especially in communication systems as we go towards higher carrier frequencies, like let's say 30 gigahertz, will need better timing. And systems like that might be useful in what the military calls GPS denied environments, or for improving robustness in the GPS system. There's only something like 30 satellites. And so I'd say that I don't know, some people think of the system as being pretty vulnerable. So if we had better, many, many better clocks around the nation, that would help to create robustness in GPS.
And talking about advancing networks and communications and the applications here, how far away do you think we might be from a whole revised idea of the internet? I'm growing up, I think of the 56K modem, and then cable comes along and blows me away, and now it's 5G. How far away are we from the next big advancement that reimagines internet as we know it?
Okay, I was wondering what you asked that, and I thought, do I have a good answer? And I think I do. One of the big problems with, let's say, going to, communications at 30 gigahertz, right? Because that's the goal. Let's say maybe it's not just internet, but it's just communications and wireless communications in general, is that we've been kind of stuck, at relatively low frequencies for a very long time, right? So these cell phones that we use operate in the gigahertz range. And to increase the speed by, let's say, 10 or 30 times has a lot of challenges associated with it. In particular, we don't have a lot of good amplifiers inside of phones that are efficient. And if you don't have efficient amplifiers, what it does is it drains batteries. So this is a big challenge for actually going to higher carrier frequencies. And so a big jump in technology would be the development of high-speed digital electronics with high efficiencies. And that would really enable like what we originally were hoping to see for like 5G technologies. And that is going to higher frequencies, which would enable higher data rates. And if you're going to a whole new frequency band that's not crammed, like the frequency bands that we have currently for communications, then you have very low latency. So latency is about, how long does it take for your signal to come back, right? So you have these kind of clogged channels. So it's not only about data rates, it's about, how fast can you get return signals from things. And so if we had low latency, we could see advances, really good advances in things like robotic surgery, right? Like the last thing you want to do is have latency in your robotic surgery where you have an expert somewhere here and, a patient, on the other side of the world, and they cut a vein and that person bleeds out, so, right. So things like that would be enabled that's what I think would be the biggest next step in terms of communication and internet.
Gotcha. Yeah. And everything wants everything faster, sooner, quicker, and it's always a challenge because then you load up servers and then things start bogging down again. But focusing on NIST, because I know NIST has a big role in developing the workforce domestically and getting more, Americans involved and picking up the torch for photonics and going through STEM. I wanted to ask, is there a disparity between kind of who is getting involved in the field and what can we do to kind of expand and make things more equitable?
Okay. I mean, I think this is a very important question because this is really about, diverse workforce development, which is important for maintaining, both national security, right? And economic growth in the United States. And I think there are a lot of contributing issues to this. One is that I think our education system is a little bit outdated. There are, I don't know what percentage there are, but for certain there are, physics isn't necessarily required even at the high school level. So we have an education issue. We also have an immigration issue. So the United States has amazing research programs that attracts foreign nationals. But, the immigration system can be challenging in terms of keeping those nationals here. So we put, US dollars into educating, right, foreign nationals, but we don't have a smart way to keep them currently. In terms of, things like diversity and equity, I'd say one of the big challenges that we have in the optics and photonics, and especially in the quantum workforce, is a lack of technicians. So it's not that we need that many PhDs, we need a lot of technicians. This is a great need for industry. But to be able to create technicians, we need to have, educational resources and curriculum at the community college level. And the big benefit of that would be that, you can increase the diversity and participation of students from lower income, right, from lower incomes, because going to community college is less financially burdensome, less of a time burden than going to a 4-year STEM degree. Well,
yeah, and we're talking about jobs too that are, in high demand and may pay more than some other entry-level positions. So going to community college, saving money and getting out into this field that has, such room for growth.
Exactly. But another issue is that if we want to increase diversity, right, we need to be able to create environments that are more inclusive. And I'd say in general that, STEM and the tech industry, right? STEM and tech industries have a kind of cultural issues, right? That can make it, unwelcoming to, let's say, underrepresented groups. So, and also we have these entrenched cultural ideas, right? That, we are, right, certain industries or certain companies are excellent because of the ways they did things in the past. And this is a fantastic way to ensure that there will be no change in the future. And this is not attractive for, let's say, underrepresented groups because they might not see themselves as being successful in these entrenched cultures. So things that we can do that are pretty simple to change are, if we sit around and we talk about, how hard we worked and that we ate dinner out of a vending machine, that's going to discourage parents maybe from participating in jobs like that. And also if we use like these old ideas of, the devil's advocate method for vetting problems, we're going to discourage participation because what we're doing is we're looking at idea generation through the lens of failure instead of through the lens of how things might work. So I feel like we can change our communication very easily around these things and change the culture, right? I mean, one thing I try to tell parents is that, STEM jobs are well paid, right? You have a lot of opportunities for things like flex time. And so that can help encourage parents to more participate, be active in STEM, especially mothers. And we can, instead of, like vetting ideas through the devil's advocate method, you can easily just say, that's a really good idea. How can we build on it? Right. And then that's, what it does is it at least acknowledges the successes in those ideas and then uses creative solutions to try to improve on it. Right. So that improves engagement and creativity and communication around problem solving.
Yeah, and a lot of advantages to be gained by tapping the potential of the entire recruitment pool, right? You don't want any one, race, creed, gender to be, gravitate towards this, right? You want everyone to have an equal shot. And I, was reading that, when kids really start to think of what I want to be when I grow up with a real serious intent is kind of around middle school. Can something be gained then to more projects that are, introduce an 8th grader to photonics? No, you're not going to understand every bit of, quantum technologies, but build the interest. Can that exposure kind of help?
Absolutely, right? Because if they don't see the opportunities, they're not going to choose to do physics and optical engineering degrees, right? And we want them to know that there are cool and high-paying opportunities in optics and photonics, right? This is definitely an important way to reach, right, students.
Going on now and carrying on with that thread, there's a big push. Photonics, a very global industry, and like so many other industries, sometimes it becomes more cost effective to import the technology. So, while we try to look towards, steps the U.S. is taking towards domestic growth, what role can NIST play to kind of support that mission to keep photonics, at home?
Well, I'd say like there's the standard things that one would say about NIST. We have, as part of our mission, the development of standards, the development of new innovative measurement techniques, and both of those help to support, let's say, the economy, right, and the creation of jobs by ensuring kind of quality in the production of products, standardization across industries, right, and interoperability between different devices. So that's an important one. But also, part of this mission also is basically government industry partnerships. So NIST actually has a lot of pass-through funding to help industry, especially small businesses, to take novel technology ideas and bring them to production. So those are some areas where the U.S. can help in terms of U.S. innovation and growth. But also NIST has a really strong, plays a really strong role in terms of workforce development because we have a lot of students, grad students and, professional interns come through NIST to get training in precision metrology. For us, it's, kind of in time and frequency metrology and in quantum. But that helps I feel like that helps very strongly to support innovation in the U.S. and the U.S. workforce.
Thinking about kind of how you got involved in this field, especially as we talk about, we're seeking more equity now, and we want to become more diverse now. What would you tell, a younger girl or a student thinking about getting into this field that maybe you would have liked to know or that would have helped you get involved in something like this?
That's a very good question. I have many answers to that question. Let me think about what's the most important one. I'd say that One thing that's important to consider is that it's, when I entered into physics, I definitely was a minority. And so I felt a little bit nervous about speaking up. But if you're excellent and nobody sees you, you're very easy to ignore. And so, being heard and being seen is very important for gaining opportunities. So I felt like one of the most important skills that I developed in my career was the ability to network. Networking is important for so many reasons. It brings you career opportunities. It brings you career stability. It gives you access to people, that you can ask questions to. It helps make your job easier. It helps you to delegate. Networking is so important. I think this is not stressed heavily enough to scientists, especially PhDs. Another thing that's very important is communication, and especially how to resolve conflict neutrally. Because I'd say that tech and PhDs can't, kind of fields where there are a lot of tech and PhDs can be pretty conflict-ridden places, and knowing how to communicate assertively and to feel comfortable, advocating for yourself, advocating for others, advocating for ideas, right? Putting your voice out there in a way that it can be heard is extremely powerful.
I think those are probably good tips anyone can take to, various professional fields. So I thank you for that. And Tara Fortier, thank you so much for joining us on the All Things Photonics podcast.
Okay, thank you so much. Thank you so much for giving me the opportunity to be here, and thank you for the thoughtful questions.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.